A month has passed since three-eyed Atlas's closest approach to Earth. It seemed all cards were on the table. But a fresh publication from December 23rd doesn't create a new theory, it creates a different reality. Meticulous calculations based on current data paint a portrait of an object 5 times smaller and 120 times lighter than previously asserted based on equally meticulous observations. This is not a refinement, this is a direct contradiction. Two scientific camps, armed with humanity's best tools, look at the same celestial body and see two different objects. The truth lies somewhere in between, but that in between is the strangest part of the story. Welcome to the mass paradox. Imagine determining the size of a jet engine by its thrust and fuel consumption. This principle underlies the December calculations. Scientists measured Atlas's non-gravitational acceleration, a microscopic yet steady boost of 13 kilometers per second each day. The source of this boost is the reactive force from gas jets. The James Webb Space Telescope acted as a super-precise flow meter, gas velocity, around 1,600 kilometers per hour, and its mass flow rate, around 150 kilograms per second. Knowing the thrust and fuel consumption, physics gives a clear answer. The diameter of the engine, that is the active nucleus releasing gas, is around 1 kilometer. Assuming the standard fluffy comet density, 500 kilograms per meter cubed, its mass is around 260 billion kilograms. This is an elegant, self-consistent picture. The object's activity perfectly explains its observed acceleration. This is object number 1, compact, active, predictable. But now we go back in time, to the period from May to September. Back then, Atlas was far from the sun. A network of 230-plus observatories with fantastic precision, able to spot a coin from 100 kilometers away, tracked its trajectory. And here is the key fact. No non-gravitational acceleration was detected. The important part is not the zero itself, but the sensitivity limit of the measurements. It was 300 times sharper than the force measured in December. If even a weak engine from a 1-kilometer nucleus had been operating back then, it would have necessarily been noticed. It wasn't. This means one thing. If the contribution of the reactive force was negligible, then to explain even the weak observed activity, the object's mass must be colossal, because the same ejection force will impart less acceleration to a heavier body. Calculations, particularly by Avi Loeb from Harvard, give the lower bound. Diameter greater than 5 kilometers, mass greater than 33 trillion kilograms. This is object number 2, massive, inert, barely responsive to the ejection of its own substance. Two portraits, a chasm between them, a factor of 5 in size, a factor of 120 in mass. This is not an error, it's the condition of the problem. Here are the keys to solving it. 1. Thrust evolution. Acceleration data since October has been constantly refined downward. If the true value turns out to be lower than the current one, the calculated size for object number 1 will increase, approaching 5 kilometers. 2. Mass loss. Between May and December, having passed perihelion, Atlas could have lost billions of tons of matter. Object number 2, May, was objectively heavier than object number 1, December. We are comparing an apple to the same apple, but already bitten. 3. The vector game, the most important. Reactive force is a vector. If from May to September the main ejection was directed perpendicular to the line of flight, it wouldn't change the orbital speed, which is what telescopes tracked, but only spun the object. By October, due to rotation and heating of new areas, the thrust vector could have turned along the trajectory, creating that very measurable acceleration. We didn't see a new engine, we saw the old one turn to face us from a different angle. 4. The anatomy of anomaly. All calculations use assumptions: average density, sphericity, uniformity of outgassing. If Atlas's nucleus is not a fluffy snowball, but a denser body with extremely asymmetric vents, then formulas for ordinary comets yield a systematic error. Its true size may lie in the dead zone between 1 and 5 kilometers. This measurement conflict is not a weakness of science, but its triumph. It points with surgical precision to Atlas's uniqueness. First, it demonstrates phenomenal activity asymmetry. The unevenness of Atlas's jets must be orders of magnitude higher than that of domestic comets to generate such uncertainty. Second, it calls into question the universality of cometary density, 500 kilograms per meter cubed. Perhaps its nucleus is bolder, but a more monolithic body of melted ice and rock that has withstood billions of years of cosmic bombardment. This would increase its density, meaning that for the same mass, it would be smaller. Third, the swarm or elongated shape hypothesis receives new momentum. Thrust is calculated for a spherical nucleus, but if Atlas is a cigar-shaped body or a swarm of fragments, the relationship between its activity, mass, and observed acceleration completely changes, invalidating the direct comparison of the two methods. The main lesson of this contradiction is that we might be asking the wrong question. We persistently try to determine the size of the nucleus, as if it's a clearly defined rock. But Atlas behaves not like a rock, but like a complex, active system. Its size is a dynamic concept. In May, its effective size for orbital mechanics was huge, 5+ kilometers, because the activity was hidden or compensated. In December, its effective size for thrust calculation became small, 1 kilometer, because we saw only one, currently dominant, active region. Instead of searching for a single number, science is now forced to build a three-dimensional map of activity over time, a model that explains how the direction and strength of jets changed with rotation and heating. The truth is not between 1 and 5 kilometers. The truth is that these two numbers are merely two projections of one immensely complex object onto different axes of measurement. The mass paradox is not a dead end. It is a compass pointing to the hidden complexity of our first interstellar guest. The mystery is just beginning.